Welcome. There is nowhere to be right now, nothing to solve, nothing to hold. Let your shoulders sink into whatever is beneath you, and let your eyes rest, half closed or fully closed, whichever feels further from thought. Tonight, we grow a whole world from something smaller than a grain of salt. We begin with birch pollen, each grain measuring only about 20 to 30 micrometers across, a golden dust drifting on spring air, invisible almost, yet carrying the first instructions for a forest. Birch bark hides tiny crystals too small for any eye to see. Betulin, a waxy compound, arranges itself into nanoscale structures within the outer layers of the bark. These crystals scatter light in a way that gives the bark its pale, luminous sheen. Under magnification, they look like frost, layered and orderly, a quiet architecture built without hands. Inside a single birch leaf, one chloroplast quietly turns sunlight into sugar. Light strikes chlorophyll molecules, and electrons begin their patient journey. Carbon dioxide and water are drawn in, and out comes glucose, the leaf's own quiet form of nourishment. It happens by the trillions in every leaf, every sunlit hour, without sound or effort. Birch leaves breathe through tiny gates called guard cells. These paired cells swell and relax, opening and closing pores called stomata. Through these small openings, carbon dioxide enters and water vapor departs, a slow rhythmic exchange between leaf and sky. Each pore is smaller than a period on a page, yet together they shape the breath of the whole tree. Betulinic acid molecules give birch bark its pale white color. These compounds reflect light rather than absorbing it, keeping the trunk cool beneath northern sun. The whiteness we admire from a distance is really a molecular choice, repeated endlessly across the bark's surface. It is chemistry quietly deciding how a tree will meet the light. Deep inside the trunk, xylem vessels carry water upward through channels finer than a hair. Water molecules cling to each other, pulled skyward by evaporation from the leaves above. This microscopic plumbing moves moisture from root to crown without a single pump, only the quiet physics of tension and cohesion working in the dark of the wood. A birch seed weighs less than 1 milligram, lighter than a whisper. You could hold hundreds in your open palm and barely feel their presence. Within that almost non-existent weight rests everything a future tree will ever need. It is one of nature's smallest promises, waiting patiently for the right conditions. Birch seeds carry small papery wings shaped for the wind. These wings are not decoration, they are engineering, catching air currents and carrying the seed far from its parent tree. A gentle breeze can lift a birch seed for meters, sometimes kilometers, scattering possibility across open ground. Each flight is brief, but it is how forests wander. Within each birch seed's embryo lies a complete genetic blueprint. Coiled strands of deoxyribonucleic acid hold instructions for roots, bark, leaves, and the particular white sheen of a birch's future trunk. It is a plan folded impossibly small, waiting inside a seed lighter than a feather, ready to unfold given warmth, moisture, and time. Birch seeds will not grow until they have felt real cold. This process, called cold stratification, tells the seed that winter has passed and spring is safe to trust. Without weeks of chill, the seed stays dormant, patient inside its papery shell. It is a quiet form of memory, written into biology, ensuring life begins only when the world is ready. Let the breath lengthen now, just slightly, on its way out. Notice how the exhale takes a little longer than the inhale, like a wave pulling back from shore. There is no need to control it, only to follow it. Each breath rolls out a little further, carrying tension away with it, leaving the body a little heavier, a little more settled with every slow release. Beneath the surface, a germinating birch seed sends its first root downward before anything else appears. This taproot searches for stability, anchoring the tiny plant before it dares to reach toward light. It moves through soil in search of moisture, guided by forces older than memory. Everything above ground will depend on this first quiet decision made in darkness. Within days of breaking through soil, a birch seedling already begins making its own food. Tiny leaves unfold, thin as paper, yet capable of capturing sunlight almost immediately. Photosynthesis begins long before the plant looks like a tree at all. It is a remarkably fast transition from stored seed energy to self-sustaining life, powered entirely by light. Each spring, a young birch sapling can grow several centimeters in a single week. This burst of growth takes advantage of longer daylight and thawing ground. Cells divide rapidly along the stem, stretching the sapling upward in visible spurts. By early summer, growth slows again as the tree settles into a steadier, more measured rhythm of living. By its third or fourth year, a birch tree begins revealing the bark it is known for. Thin outer layers start to peel away, exposing pale, papery surfaces beneath. This transformation happens gradually, patch by patch, until the trunk carries its familiar white sheen. What was once ordinary brown bark becomes something almost luminous against a darkening forest. The petulin inside birch bark does more than shape its pale color. This waxy compound also discourages insects from settling too comfortably on the trunk. Its chemical structure interferes with certain pests, offering the tree a quiet form of protection woven into its own skin. Nature here has built defense and beauty from the very same material. A mature birch leaf performs a small, continuous miracle each daylight hour. Sunlight, water drawn up from roots, and carbon dioxide from the air combine inside its cells to produce sugar and oxygen. This exchange happens silently, thousands of times across a single tree. In every leaf, every day, the sun is out. It is invisible work sustaining visible life. Birch roots spread wide across the earth, rather than reaching deep into it. This shallow, sprawling structure lets the tree gather water and nutrients from a broad area near the surface. It also helps birch trees establish quickly in soils where deeper roots would struggle. Strength, for this tree, comes from breadth rather than depth. Underground threads of fungi wrap around birch roots, forming a partnership neither could easily replicate alone. These mycorrhizal networks extend the root system's reach far beyond what the tree could manage on its own, trading sugars for minerals and water. It is an ancient alliance, invisible from above, quietly shaping how well a birch tree can thrive. Over the course of its life, a single birch tree may release more than 1 million seeds. Most will never find suitable ground, carried instead by wind to places unsuited for growth. Yet this abundance is the strategy itself, a wide scattering of possibility across the landscape. From one tree's lifetime, an entire future forest becomes statistically almost inevitable. 60 to 90 years marks the typical span of a birch tree's life, brief compared to an oak or a redwood. Within that window it grows, flowers, scatters seed, and eventually gives ground to slower, longer-lived trees that follow. This shortness is part of its purpose. Birch opens a path for the forest that will outlast it, then steps aside without complaint, its work already finished. Feel the weight settle into your legs now, heavy and unhurried, sinking into whatever is holding you. Let that heaviness spread upward, through your hips and your back, resting fully into the mattress beneath you. Your shoulders loosen and drop. Your arms grow warm and still, palms open, fingers slack. There is only this weight, and the dark and the slow rhythm of breath moving in and out, asking nothing of you. Birch wood grows with a fine, even grain, prized by builders for its strength and predictability. Under close view, its fibers align in tight, orderly rows, giving the timber unusual stiffness for its weight. Furniture makers value this consistency, as do makers of plywood and skis. What looks like a pale, unremarkable wood carries, at the fiber level, a subtle kind of order beneath its plainness. Disturbed soil, the kind left behind by fire, flood, or fallen forest, is where birch trees arrive first. They are called pioneer species, thriving where little else can, tolerating poor ground and open sun. Their roots stabilize loose earth while their fallen leaves begin rebuilding what was lost. Long before slower trees return, birch has already begun the work of mending the land. Hundreds of liters of water can pass through a single birch tree in a single day, drawn from the soil and released into the air as vapor. This transpiration cools the tree and the air around it, pulling water endlessly upward through countless microscopic vessels. Multiply this across a whole grove, and the invisible traffic of water becomes vast. A birch forest breathes water the way lungs breathe air. Far below the forest floor, birch trees form partnerships with fungi, able to draw nitrogen from the air and deposit it into the soil. The amounts are modest, tree by tree, but across a stand they accumulate, slowly enriching ground that would otherwise stay thin and poor. Nitrogen, essential for growth, arrives not through birch alone, but through this exchange with partners unseen. Catkins hang from birch branches in early spring, releasing fine clouds of pollen that ride the wind for kilometers. Each grain is light enough to travel far past its parent tree, carried over fields, rivers, and rooftops before settling. Most will never reach a receptive flower, but enough will, scattered widely enough to keep birch populations connected across whole landscapes. The wind, in this sense, is also a gardener. A few birch trees, standing together for even a handful of years, begin changing the chemistry of the soil beneath them. Fallen leaves and shed bark decompose, adding organic matter and shifting acidity in small, measurable ways. Nutrients once locked in rock or old vegetation become available to nearby plants. A modest stand of birch, without any grand design, starts rewriting what the ground beneath it can support. Small groves of birch create pockets of shade and moisture noticeably cooler than the open ground around them. Their canopies filter sunlight, their trunks block wind, and their transpiring leaves release cooling vapor into the surrounding air. Step from an open field into even a modest birch grove, and the temperature seems to drop by several degrees. A cluster of trees, it turns out, can carry its own climate. Moisture gathers more thickly within a birch grove than across the open land nearby, lifted continuously from countless leaves into the air. This raised humidity supports mosses, ferns, and fungi that could not survive in drier conditions just meters away. A birch grove, then, does more than stand within a landscape. It steadily reshapes the air itself, one leaf's breath at a time. Each year, the birch releases its foliage back to the forest floor, and there it slowly breaks down into the soil below. Fungi and small organisms work through the fallen material, releasing nitrogen, phosphorus, and other nutrients locked within its cells. This steady decay builds a dark, crumbling layer, rich enough to nourish generations of seedlings. What once hung high in the canopy becomes, in time, the ground itself. Tiny insects called leaf miners spend much of their short lives tunneling inside birch foliage, tracing pale winding paths as they feed. Their larvae carve intricate galleries between the upper and lower surfaces, invisible until held to the light. Birds and other insects, in turn, depend on these miners as a steady food source. A birch stand, then, hosts entire hidden lives within its living tissue. Somewhere outside, a low hum rises and fades, carried on shifting air. It might be wind moving through distant branches, or a house settling into the hour, its old wood easing under the weight of night. The sound arrives without asking anything of you and leaves the same way. There is no need to follow it, only to notice it drifting past and let your breath grow longer with each pass. On sloped ground, a young birch grove sends roots outward and downward, binding loose soil into a firmer mass. Rainwater that might otherwise carry earth downhill instead meets a lattice of fine roots holding it in place. Over a handful of seasons, bare, shifting hillsides settle into something steadier. The trees ask for little, yet they quietly hold the land together beneath their branches. Beneath the birch canopy, light arrives in shifting patches rather than steady streams, and certain plants have adapted precisely to this rhythm. Ferns, wood anemones, and low woodland herbs unfurl in these dappled pockets, drawing what sunlight filters through moving branches above. Too much shade would starve them, too much sun would scorch them. The forest floor becomes a mosaic tuned exactly to what the canopy allows through. Threading through the soil of a birch woodland, fungal networks stretch for astonishing distances, linking tree to tree in a hidden lattice. These mycelial strands trade sugars for minerals, moving resources between individuals in ways still not entirely mapped by science. A single network beneath one grove can span far wider than the trees themselves ever touch above ground. The forest, in this sense, is as connected below as it is separate above. A single hectare of birch forest, roughly the size of a large park, can draw several tons of carbon from the air each year. Leaves, wood, and roots all lock this carbon into living tissue, storing it long after it leaves the atmosphere. Multiply this modest patch across a whole landscape, and the numbers grow into something far larger. A birch forest quietly becomes a slow engine for pulling carbon out of the sky. Across a whole landscape, birch forests bend and slow the wind, their trunks and canopies acting as a loose, living barrier. Air that would otherwise sweep unbroken across open plains instead meets resistance, splitting into gentler currents near the ground. Snow drifts differently near forest edges, and seeds travel shorter distances downwind. What begins as a single tree shade becomes, at scale, a force shaping the movement of air itself. From above, birch canopies appear pale and luminous compared to the deep green of conifer forest nearby, and this brightness carries real consequence. Their lighter foliage reflects more incoming sunlight back toward the sky, keeping the surface beneath slightly cooler than darker forest types. Across vast stretches of the north, this difference in reflectivity subtly shapes regional temperature. A forest's color, it turns out, is never just decoration. After fire sweeps through a forest, or machines clear it entirely, birch is often among the first trees to rise again from the blackened ground. Its light seeds travel easily onto bare soil, and its seedlings tolerate the harsh sun-exposed conditions left behind. Within a few short years, slender white trunks reclaim what flame or blade once stripped away. Recovery, for birch, seems written into its very nature. Woodpeckers hollow out nesting cavities in aging birch trunks, and long after they move on, those same hollows shelter owls, squirrels, and bats. Voles tunnel through the loose litter at ground level, feeding on seeds and roots. Harriers nibble young shoots in winter when little else stays exposed above the snow. A birch woodland, layer by layer, becomes a shared address for hundreds of small lives. Over decades, a birch forest builds a soil profile with visible layers, each one telling part of the story above it. Near the surface, a dark band of decomposed litter feeds the roots directly overhead. Below that, minerals shift and settle into paler bands shaped by rainfall, moving slowly downward. Dig a narrow trench through birch ground, and you read years of quiet accumulation like pages stacked one atop another. In parts of the boreal north, birch forests spread across hundreds of square kilometers without a clear edge, one stand blending into the next. Rivers and lakes interrupt the pattern here and there, but the pale trunks return again beyond each shoreline. Flying above these regions, a traveler could watch birch canopy roll past for many minutes without change. Scale, at this size, stops feeling like a forest and starts to resemble a landscape unto itself. Let warmth begin at the crown of your head, spreading down like sunlight, finding its way through branches. Feel it move into your forehead, loosening whatever tightness gathered there through the day. It flows down through your jaw, your neck, resting for a moment in your shoulders before continuing lower. Let it pool in your chest, your arms, your hands, until your whole upper body feels heavy and warm, held from the inside. Trees breathe water into the sky through millions of small pores, and across a whole birch region, this exhaled moisture becomes part of the local weather. Water lifted from soil rises through trunks and leaves before drifting upward as vapor. That vapor gathers into clouds, and clouds, in time, return the water as rain somewhere downwind. A forest, it turns out, helps write its own forecast. As glaciers retreated thousands of years ago, bare rock and gravel lay exposed across huge stretches of northern land. Birch was among the first trees able to root into this raw, mineral-poor ground. Its light seeds drifted onto terrain where almost nothing else could yet survive. Long before deeper forests followed, birch had already begun softening the land for what would come after. North of the temperate world lies the taiga, a forest belt encircling the globe just below the Arctic. Birch grows throughout this vast region, often mixed among spruce, pine, and larch. Together, these trees form one of the largest continuous forest systems on Earth. Standing among its birch stands, a traveler is really standing inside a belt of trees that wraps most of the planet's northern half. Scientists studying satellite imagery describe a circumboreal forest belt, a ring of trees stretching almost unbroken around the top of the world. Within this ring, birch appears again and again, threading through Scandinavian hills, Siberian lowlands, and Canadian plains alike. Different nations, different languages, and yet the same pale trunks rise from similar cold, glacier-shaped soil. Geography, at this scale, seems to matter less than climate and light. From the fjords of Scandinavia to the river valleys of Siberia and onward across the cold plains of North America, birch trees have made themselves at home. Each population adapts slightly to its own local light and frost pattern, yet all remain recognizably the same pale-barked tree. A birch seedling in Norway and one in Alaska share more in common than the vast distance between them might suggest. The same simple design, tested and repeated across an entire hemisphere. Across whole continents, birch forests draw carbon from the air and store it in wood, roots, and slowly accumulating soil. This stored carbon shifts the balance of gases moving between land and atmosphere on a regional scale. Where birch forests expand, that balance tips further toward storage. Where they shrink, it tips the other way. A single tree's quiet chemistry, repeated across millions of trunks, becomes a force shaping the air over an entire landmass. Large-scale birch afforestation could shift how much sunlight a whole region reflects back into space. Bark that stays pale through winter brightens a landscape that might otherwise appear dark with conifer cover or bare soil. Foresters studying reflectivity call this quality albedo. Where birch spreads across hillsides and valleys, the ground itself seems to lighten, catching more daylight and returning more of it skyward. A small shift in color, repeated across kilometers, changes how a region trades warmth with the sky above it. Rivers threading through birch country carry more than water. They carry the health of the land around them. Watershed hydrologists have long noted that birch roots hold soil in place along riverbanks, slowing erosion and filtering runoff before it reaches the current. Across a whole continent, this pattern repeats itself in thousands of small tributaries. A river fed by birch-lined slopes tends to run clearer, its sediment reduced by countless unseen roots that hold the land in place. Under the boreal birch belt, frozen ground called permafrost holds carbon and water locked away for thousands of years. Birch roots and canopy shade affect how much warmth reaches that frozen layer each summer. Ecologists studying the Arctic describe a delicate balance. Too much birch removal exposes permafrost to faster thaw, while healthy stands help insulate the ground beneath them. The relationship between a slender white tree and ground frozen since the last ice age remains an active field of study. Wide belts of birch forest can bend and slow the wind moving across open land. Foresters in windswept regions have long planted birch as a living barrier, breaking storm gusts before they reach fields and settlements. At a larger scale, entire forest belts appear to influence regional wind patterns and even the paths of passing storms. A tree that seems delicate up close turns out, in great numbers, to reshape the very air moving over a landscape. Somewhere in a warm, low-lit room, dust hangs in a single beam of light, moving so little it seems almost still. Watch it long enough, and you stop noticing time passing at all. Let your breath match that drift, unhurried, weightless, going nowhere in particular. Your shoulders can rest into whatever is holding you now. Let your eyes close the way that beam of light eventually fades from a window at the end of a long afternoon. Global tallies of forest carbon rely heavily on birch and its boreal neighbors, since these northern woodlands cover such staggering distances. Climate scientists building planetary carbon models must account for how much birch canopy exists, how fast it grows, and how long its wood holds carbon before decay or fire returns it to the air. A change in birch cover on one continent can nudge an estimate for the whole planet. The tree's story in this sense is written into equations meant to describe an entire world's breathing. Beyond Earth, building a birch planet would first require air thick enough to hold weight and warmth against a tree's branches. Atmospheric engineers imagine adjusting pressure long before a single seed is planted, since birch, like all earth plants, evolved within a narrow range of surface pressure. Too thin an atmosphere and water boils away before it reaches roots. Too thick and sunlight struggles to filter through. Getting this balance right stands as the first engineering problem of an otherwise living dream. A birch-dominated world would need air built mostly of nitrogen, laced with enough oxygen to support growth and breath. On Earth, this balance formed over billions of years through the slow work of early life. On a new planet, engineers would need to manufacture it directly. Too little oxygen and birch cells cannot respire efficiently. Too much invites uncontrolled fire across a forest planet. Recreating Earth's familiar air recipe becomes an essential step before a single birch stand could ever take root. Every birch tree depends on liquid water moving up through its trunk, which means any birch planet needs a hydrosphere that stays liquid rather than frozen or boiled away. Engineers would need oceans, rivers, or at least reliable groundwater cycling through soil and roots. Without steady rainfall or irrigation, birch seedlings simply could not survive their first fragile years. Water, more than almost anything else, decides whether a distant world could ever host a forest at all. A birch planet's average temperature would need to sit somewhere between about -5 and 25 degrees Celsius. The range birch trees have adapted to across their entire earthly range, colder, and growth stops before it starts, hotter, and the tree's cool climate biology begins to fail. This modest window, wide enough to include Scandinavian winters and Siberian summers, would define much of a birch planet's climate design. A tree that seems humble turns out to set strict terms for an entire world's thermostat. Light itself carries a rhythm that birch trees have learned to read across countless generations. Lengthening days in spring signal buds to open, while shortening autumn light tells leaves to fold their green away. Without this seasonal shift, a birch cannot properly time its growth, its dormancy, or its slow gathering of strength for winter. Any world hoping to grow birch forests would need days that lengthen and shorten in a familiar, dependable rhythm. Tilt, more than distance from a star, decides whether a planet feels seasons at all. A world spinning nearly upright on its axis might bake evenly year-round, offering birch no signal to grow or rest. A gentle lean, closer to Earth's own 23 degrees, lets sunlight sweep north and south through the year, creating the seasonal pulse birch biology has always depended upon. Tilt becomes destiny for a forest planet. Laboratories on Earth have already begun adjusting birch genetics for futures its ancestors never faced. Researchers exploring gene editing suggest birch seeds might be modified to respire efficiently even where oxygen runs thinner than our own atmosphere provides. Such seeds could germinate on a world still finishing its atmospheric buildup, tolerating margins that would stress an ordinary tree. Engineering resilience into a seed becomes one way of preparing life for an unfinished sky. Long before any sapling could take root, engineers would need to seed a planet's soil with mycorrhizal fungi, the hidden partners birch trees have relied upon for millions of years. These fungal threads help roots draw water and minerals from ground that would otherwise resist them. Introducing fungi first means giving birch an invisible support system waiting underground, ready the moment seeds arrive. A forest's success may depend on this quiet, unseen head start. Centuries, not seasons, would likely pass before a barren planet's ground could hold a forest at all. Bare rock must first weather into fine particles, mix with organic matter, and develop the layered structure that soil scientists call horizons. Only after this slow architecture forms could birch roots find purchase, moisture, and nutrients enough to survive. Soil, patient and unglamorous, becomes the true foundation beneath any imagined forest world. Let your face rest now, the way still water rests once the wind has passed. Let your jaw loosen, your lips part just slightly, no need to hold any shape at all. Feel the weight settle behind your closed eyes, heavy and low, like curtains drawn against a bright afternoon. Nothing in your expression needs to do anything right now. Just let it soften, fold by fold, into the dark behind your eyelids. Before any tree could dream of standing there, lichens would need to arrive first. Tiny pioneers spreading across bare regolith like a patient green stain. Mosses would follow, holding moisture against stone and slowly breaking mineral surfaces into something closer to soil. This first wave of small, humble organisms prepares ground that no birch seed could otherwise survive upon. Forests, it turns out, always begin with the smallest and least noticed of settlers. Heat, in the earliest chapters of a birch planet story, might need to come from gases engineers choose to release on purpose. Carbon dioxide and methane, carefully calculated rather than accidental, could trap enough starlight to lift a frozen world above freezing. This borrowed warmth would only be a beginning, a bridge, until forests themselves could help regulate climate. Sometimes the first breath of warmth on a new world comes from careful, deliberate design. High above a cold, struggling world, engineers imagine positioning vast mirrors to redirect sunlight exactly where it's needed most. Focused light falling on chosen valleys could raise local temperatures enough for birch seedlings to photosynthesize through otherwise dim, sunless months. Orbital mirrors would act like patient hands, cupping extra light toward hesitant young forests. A distant star's rays, gathered and aimed, might coax green life from stubborn cold ground. Ultraviolet light, unfiltered by a thin or forming atmosphere, could damage birch cells before an ozone layer ever develops. Genetic engineers imagine strengthening birch neon repair systems and reinforcing leaf pigments to withstand this early exposure. Such modified trees might tolerate the harsher light of a young planet's uncertain sky. Resilience bred into birch cells becomes a quiet form of protection, letting forests survive the years before the sky learns to shield them properly. An ozone layer, thin and invisible, would need to form high above a young birch world before its forests could truly thrive. This shield of oxygen molecules, split and rejoined by sunlight, filters out the harshest ultraviolet rays. Without it, birch leaves would blister under radiation. No atmosphere yet blocks. Planetary chemists imagine seeding early oxygen production specifically to hasten this protective layer's arrival, so forests below might finally stand unguarded. A planet's magnetic field, generated deep within its molten core, determines whether any atmosphere survives long enough for birch forests to breathe. Solar wind, unchecked, strips lighter gases away over millions of years, leaving worlds bare and dry. A strong enough field deflects these charged particles, holding oxygen and nitrogen close to the surface. Terraforming engineers weigh a candidate world's core activity as carefully as its distance from any star. Pollinating insects, carried across the void in sealed containers, would need release long before birch forests could reproduce on their own. Wind alone spreads pollen, but cross-pollination and genetic mixing often depend on small winged visitors moving between distant groves. Bees, moths, and beetles bred for resilience might be chosen first, tested against a new world's air and light. Without them, birch populations could drift toward fragile sameness rather than the rich variety forests need. Nitrogen-fixing bacteria, invisible to the eye, would need introduction into planetary soil long before birch roots could draw real nourishment from it. These microscopic partners convert nitrogen from the air into forms plants can use, a service birch trees depend upon through their fungal allies. Bare regolith, however rich in minerals, holds none of this hidden chemistry naturally. Seeding soil with such bacteria becomes an early, essential act, invisible work laying groundwork for visible forests. Across many generations, wide birch planting could raise a planet's oxygen levels measurably, though the process unfolds over centuries rather than seasons. Each leaf performs its small exchange, drawing in carbon dioxide and releasing oxygen into thinning air, multiplied across billions of trees and hundreds of years. This exchange gradually reshapes what a planet's atmosphere contains. Forests, in this sense, become slow architects of the very air that later life will breathe. Birch forests, in many terraforming plans, represent only the opening stage of a longer succession meant to unfold over generations. Pioneer trees stabilize soil and moderate climate, preparing conditions for other species that could never survive a planet's harsher early years. Conifers, oaks, and eventually more delicate plants might follow once birch has done its quiet groundwork. A birch planet, then, is not an ending but a careful beginning, one chapter in a much longer ecological story. Let your breath find its own unhurried rhythm now. No need to guide it, only to notice it arriving and leaving. Each inhale rises without effort. Each exhale lengthens a little more than the one before it. There is a kind of drifting that begins exactly here, in the space between one breath and the next. Let the exhale carry a little more of the day's weight away each time, until breathing itself feels like the only task left, and even that grows distant. Indeed, engineers often name birch a first responder for excess carbon, a species suited to drawing down what a young atmosphere holds in surplus. Its rapid growth and dense root systems capture carbon efficiently compared to slower-growing trees. Vast birch plantations, spread deliberately across barren terrain, could function almost like living machinery built for atmospheric repair. Choosing birch first in many terraforming models comes down to this remarkable appetite for carbon. How long a day lasts on a birch planet depends entirely on how quickly that world spins beneath its star. A slow rotation might grant birch trees long stretches of light, followed by equally long darkness, testing their tolerance for extremes. A faster spin offers shorter, gentler cycles closer to what Earth's forests have always known. Photosynthesis itself bends to this rhythm, leaves working only when light allows, resting through whatever darkness follows. Spread wide enough across a planet's surface, birch cover could steadily draw down atmospheric carbon dioxide until the very climate shifts beneath it. Each tree removes only a small amount, but multiplied across continents and centuries, the effect compounds into something planetary. Cooling follows gradually, as greenhouse gases thin and starlight escapes more easily back into space. A world once trapped in its own heat might, through birch alone, begin to breathe more easily. White bark once served a single birch tree well, bouncing away excess sunlight to protect its trunk from scorching. Multiply that same brightness across an entire planet's surface, and something larger happens to the whole world's balance of light. Bare rock and dark soil absorb heat readily, but pale birch canopies send more of that starlight straight back toward space. A forested world dressed in silver and pale green could run cooler simply by reflecting more of what falls on it. Trees are not passive against moving air, they reshape it as it passes over them. Rough canopies slow winds near the surface, while open plains let air rush unhindered across the ground. Across an entire birch-covered world, this friction would ripple outward, bending jet streams and reshaping storm paths that once moved freely over barren terrain. Weather itself would learn a new rhythm, shaped by millions of trembling leaves. Every leaf releases a small breath of water vapor into the air, cooling itself the way sweat cools skin. A forest performs this exchange endlessly, exhaling moisture through countless stomata scattered across its canopy. Multiplied across a planet's full expanse of birch, this quiet exhalation could steady surface temperatures, tempering both midday heat and the deep chill of long nights. Evapotranspiration becomes, at this scale, a kind of planetary thermostat. Rain falling on a birch planet would rarely stay long on the surface. Roots would draw it upward, leaves would release it again as vapor, and clouds would form anew above the very forests that fed them. Billions of trees, each pulling water from soil to sky, would together drive a cycle far larger than any single storm. Rivers, lakes, and rainfall would all trace back, in some measure, to the breathing of the forest itself. Deserts spread when soil loses moisture and roots no longer hold it in place. Birch, with its wide, shallow root systems and fast growth, could be planted deliberately along the fragile edges where forest meets open ground. Row by row, these engineered belts would slow the advance of dry terrain, anchoring soil and drawing down what little water remained. A continent once shrinking toward barrenness might instead hold its line, green pressing steadily outward. Soil is never just mineral and water. It is alive with organisms too small to see, and a barren planet would begin with none of them. Bacteria, fungi, and countless microscopic partners would need to be carried from Earth and introduced deliberately into new ground. Only once this hidden community took hold could birch roots find the nutrients and partnerships they depend on. A forest's health begins, invisibly, in what lives beneath it. A forest built from identical trees carries a hidden fragility, since a single disease or shifting climate could threaten every tree at once. Genetic variation offers something like insurance, giving different birch lineages different strengths against cold, drought, or disease. Planetary architects would need to plant not one birch but many, drawn from scattered origins across Earth's own forests. Diversity, quietly, becomes the difference between a forest that endures and one that vanishes together. Let the weight of your body settle now, layer by layer, into whatever is holding you. Feel your feet grow heavy first, sinking a little deeper into the mattress beneath them. Let that heaviness climb upward, through your legs, your hips, your lower back, each part releasing its hold on the day. Your shoulders loosen next, then your arms, then your hands, until even your head rests fully, entirely supported, needing nothing further from you. A single birch species spread across an entire world would offer disease little resistance once it arrived. Pathogens that might harm only a handful of trees on Earth could, in a monoculture stretching across continents, move unchecked from one identical tree to the next. Whole forests could weaken together, their uniform vulnerability turning against them all at once. Vast sameness, however orderly it looks from orbit, carries its own quiet risk. Resilience often comes from company rather than uniformity. Willow, thriving in wet ground, and pine, tolerant of poorer soils and colder edges, could be woven between birch stands to fill gaps birch alone cannot cover. Each species draws on different strengths, different tolerances, different relationships with fungi and insects. A planet planted this way would resemble less a single crop and more a living tapestry, each thread supporting the others. A newly forming birch biosphere could not yet feed itself. Before soil communities settle into balance, engineers would need to circulate nutrients artificially, nitrogen, phosphorus, trace minerals, moving them through pipes and sprays until fungi and bacteria take over the task. This scaffolding of chemistry would support the first fragile roots. Life would learn to feed itself over time, and the artificial cycle would fade into the background. High above the surface, orbiting agricultural stations could cultivate birch seedlings long before any planetary soil exists. Rows of saplings would grow under controlled light, their roots held in nutrient gel rather than earth. Once grown sturdy, these young trees could descend by transport craft, ready for transplant. A forest in this way might begin its life in orbit before ever touching ground. Circling far above the clouds, seed dispersal satellites could release birch seeds across vast stretches of terrain in single passes. Guided by wind and gravity models, each seed would fall toward regions chosen for soil, light, and moisture. Thousands of hectares could be seeded within days, rather than years. From orbit, the falling seeds would look like a slow, deliberate kind of rain. Across rugged terrain, no human could easily reach. Drone swarms could plant billions of birch seeds with steady precision. Each drone would carry its own small share of seed, depositing them at measured depth and spacing. Together, the swarm would move like a scattered flock, covering mountains, valleys, and plains in a single coordinated season. Work that human foresters would need generations to complete could unfold in weeks. Terraforming a birch planet is not measured in seasons, but in centuries. Establishing atmosphere, soil, and forest cover would likely require methodical, unhurried work spanning many human lifetimes. Early planners would design systems meant to outlast their own careers, handing progress forward like a relay. Across such spans of time, forests would grow not for the builders themselves, but for those who came generations later. The atmosphere of a birch planet would begin as something engineered, gases pumped, mixed, and monitored by machine. As forests spread and soils matured, biological processes would slowly assume the balance instruments had previously maintained. Sensors would gradually step back as leaves and roots took over their function. Centuries later, breathing forests, not machines, would keep the air in equilibrium. Modeling birch forest carbon capture would let planners estimate how long stabilization might take. By tracking how much carbon each hectare absorbs, engineers could project curves stretching across decades and centuries. These models would help decide where forest should grow first and how densely. Numbers on a screen, in this way, would shape the future climate of an entire world, one careful calculation at a time. Steep mountainous terrain would demand careful attention from Birch Planet architects, since forests alone cannot always hold shifting slopes together. Engineers would model rainfall, root depth, and soil composition to predict where erosion might strip young ecosystems bare. Terraces, retaining structures, and staggered planting patterns could slow the loss of soil before roots grow deep. Without such modeling, whole hillsides could wash away before the forest takes hold. Somewhere beyond the edge of hearing, a low hum rises and fades, like wind moving through a distant stand of trees. It does not ask anything of you. Let it come closer, then let it drift away again, following its own rhythm. Your breath can follow that same slow rise and fall, in and out, needing no direction from you. Rest here, inside that hum, for as long as you like. Young planets rarely stay still beneath their forming forests. Volcanic activity could release ash, heat, and sudden shifts in soil chemistry that threaten birch stands still finding their footing. A single eruption might undo years of careful planting in a matter of hours. Planners would need to map fault lines and magma flows as carefully as they map rainfall, choosing safer ground for the earliest forests to take root. Poles on a birch planet might stay locked in ice long after the equator turns green. Cold light angles and thin atmospheres would keep polar regions hostile to root growth, even as warmer belts filled with canopy. This division would mirror old patterns from Earth's own past, where forests crept toward the tropics while ice held the far north and south. A planet, in this way, could wear two faces at once. Latitude would shape the character of forest across the whole world. Near the equator, birch might grow dense and tall, while higher bands thinned into scattered groves, mixed with hardier companion species. Each stripe of latitude would carry its own rhythm of light and cold, and its own mix of trees suited to that rhythm. Walking from one band to another might feel like walking through centuries of different forest. Orbiting mirrors could carve artificial seasons into a birch planet sky. Reflectors positioned above certain regions might direct extra sunlight toward colder zones, coaxing forests to grow where natural light alone would fall short. Engineers could dim or brighten these mirrors to shape rainfall, frost, and growing seasons by design. A planet's climate, under such care, would become something tended rather than simply given. Forests spanning a planet would need open corridors cut through their reach, breaks wide enough to stop fire in its tracks. Without such gaps, a single spark carried by wind could travel unchecked across continents of birch, turning centuries of growth to ash in days. Planners would trace rivers, ridge lines, and cleared paths into the forest shape from the very beginning. Even a living world needs room to breathe between its trees. Rivers threading through a birch planet would need banks shaped with care, not left to flood at random. Engineered floodplains could let seasonal waters spread gently across low ground, feeding riparian groves that depend on that rhythm of wetting and drying. Too much water, unchecked, might drown young roots. Too little, and the groves along the banks would wither. Balance, here as everywhere, would decide whether the forest thrived. Satellites drifting above a birch planet would watch its forests, the way a caretaker watches a garden from a window. Sensors could read the color and density of leaves from orbit, flagging patches turning brittle or brown long before any walker on the ground might notice. This distant watching would let planners respond early, sending water, nutrients, or new plantings to wherever the forest showed strain. Care from that height would look like light falling on data. Seen from far above, a fully forested birch world might glow with a strange, gentle color. White bark scattered among green leaves could blend into a pale silvery green when viewed from orbit, unlike the deep blues and browns of Earth. Passing travelers might mistake it, at first glance, for a world wrapped in frost until the shifting seasons revealed the leaves beneath. A planet's color, it turns out, can be its own kind of signature. Herbivores and predators on a birch planet would need numbers kept in careful balance. Too many grazing animals might strip young saplings before they had a chance to root, while too few predators could let those populations grow unchecked. Ecologists would watch these relationships the way one watches a scale, nudging populations gently through seasons and generations. A forest's survival would depend as much on animals as on the trees themselves. A birch planet's forests could draw carbon from the sky at a scale matching Earth's own boreal belt. Across billions of trees, each hectare pulling tons of carbon from the air every year, the combined effect could shift an entire atmosphere's chemistry over centuries. This slow drawing down of carbon would echo work already happening across Siberia and Canada, only stretched across an entirely new world. What one forest does quietly, a planet's forest could do at civilizational scale. Let warmth begin somewhere small, at the center of your chest, and let it spread from there. Feel it move outward into your shoulders, loosening whatever they have carried through the day. Let it travel down each arm, reaching your fingers until they rest heavy and unmoving. Let it settle into your stomach, your hips, your thighs, sinking further with every breath. Let it reach your knees, your ankles, your feet, until warmth has filled you entirely and there is only rest. Beavers, or creatures suited to a similar role, could be introduced to shape a birch planet's wetlands. By felling small trees and damming streams, they would create shallow pools where water lingered longer across the land. These pools would draw birch seedlings to their edges, where roots could drink freely. A single industrious species working through generations might sculpt entire valleys into mosaics of marsh and grove. A moon circling a birch planet would pull gently at its oceans, shaping tides that reach into coastal forests. Where birch groves met the shoreline, roots would learn to tolerate the rhythmic rise and fall of salted water. Without a moon, coastlines might stay calmer, but also less enriched by the mixing tides bring. Even a small orbiting body, distant and pale, could leave its signature in the shape of a forest's edge. Orbital habitats supporting a birch planet's early colonists would rely on closed-loop life support, recycling every breath and drop of water. Air scrubbed of carbon dioxide by algae tanks would cycle back through sleeping quarters and greenhouses alike. Nothing could be wasted where resupply meant years of travel. Inside these stations, small birch saplings might grow under artificial light, waiting for the day their roots would touch real soil. Turning a barren planet into a birch world would demand more than decades of effort. Centuries of sustained investment, spanning generations of engineers and planners, would be needed to see the project through. Budgets would stretch across lifetimes, inherited by children who never met the founders. A forest planted with such patience would become less a project and more an inheritance passed hand to hand. Preserving the genetic diversity of Earth's birch species would matter as much off-world as it does here. Seed banks holding countless varieties, from mountain birches to lowland ones, would guard against the fragility of a single bloodline. Without this diversity, a distant forest could stumble against a disease no single strain could resist. A vault of seeds, kept cold and still, would become a quiet insurance policy for an entire world's future. A young birch planet's atmosphere might arrive not from its own crust, but from the icy comets brought to it. Comets, rich with frozen water, could be steered toward the surface to release their contents as vapor and rain. Over time, this imported water would fill rivers and lakes where none had existed before. What began as distant ice, drifting for eons through the dark, would end as rainfall on a birch sapling's leaves. Minerals drawn from asteroids could enrich the thin soils of a new birch world. Metals and trace elements mined from tumbling rock far from any star's warmth would be processed and scattered across barren ground. Birch roots, reaching into this amended Earth, would find nutrients otherwise absent from raw planetary crust. A forest's health, in this way, could trace itself back to fragments, once drifting silently between worlds. Given enough time, a birch planet's biosphere would settle into a balance that sustains itself without constant intervention. Predators and prey, forests and fungi, water and air would each find their measure against the others. Engineers who once monitored every variable might, generation by generation, step back from their instruments. A forest that no longer needs tending has, in its own way, become truly alive. Terraforming a birch forest could serve as a rehearsal for colonizing distant exoplanets. Lessons learned here about soil, water, and light would carry forward to worlds circling unfamiliar stars. Mistakes made on a nearby birch planet would become the cautionary notes for missions still generations away. In this sense, a single forest's slow growth would double as a lesson written for planets not yet reached. Keeping watch over a birch planet's temperature would remain a constant task long after the forests took hold. Sensors scattered across continents and oceans would track the smallest shifts, guarding against warming that might spiral beyond control. A tenth of a degree, unnoticed for too long, could tip a stable world toward crisis. Vigilance, patient and unending, would be the quiet price of keeping a young world in balance. Dust motes hang suspended in a beam of pale light through a window, unmoving, unhurried, each one holding its place in the stillness. Nothing asks them to fall faster or rise higher. They simply float, caught between floor and ceiling, weightless in the hush of a room at rest. Let your own thoughts hang like that tonight, suspended, unclaimed, needing nowhere further to travel. The body settles low into the mattress, heavier with every breath, while the mind drifts into that same unhurried, floating stillness. Space elevators, long cables anchored to a planet's surface and stretching into orbit, could carry birch biomass and equipment up and down without rockets. Bundles of timber, harvested seedlings, or soil samples might ride these threads in slow, steady climbs. Engineers imagine such structures replacing costly launches with a continuous, almost silent exchange between ground and sky. A birch world's forests, in this vision, would connect directly to the stations circling above them. Wood grown across a birch planet's forests could eventually supply timber for structures built far beyond its own atmosphere. Off-world colonies, orbital habitats, and distant outposts might rely on birch lumber prized for its strength and lightness. Harvested selectively, such forests would function as both ecosystem and industry, feeding construction projects light years from where the seeds first sprouted. A single tree's growth would ripple outward into buildings it will never see. Protecting a birch planet's forests would require laws written specifically for its living systems, not borrowed wholesale from Earth's old statutes. Councils overseeing such a world might set limits on harvesting, define protected groves, and regulate how quickly new land could be cleared. Environmental governance in this setting becomes as essential as any engineering plan. A forest's survival across centuries would depend as much on policy as on soil and light. Choosing a birch planet begins, often, with its star. Astronomers favor stars whose brightness holds remarkably steady across billions of years, avoiding the flickers and surges that could destabilize a young forest's climate. A star prone to sudden shifts offers little promise for centuries of stable growth. Stability, more than brilliance, becomes the quality terraformers search for first when scanning distant systems for a future home of birch. Light itself carries meaning for birch leaves. Stars resembling our own sun cast a spectrum closely matched to what birch chloroplasts evolved to absorb, making such stars ideal hosts for transplanted forests. A star burning too blue or too red would leave birch leaves straining to capture usable energy. The color of starlight, faint as the difference may seem, decides whether a forest thrives or merely survives. An orbit suited to birch life must sit within a narrow band around its star, close enough to receive warmth, distant enough to avoid scorching extremes. Too near, and water boils away before roots can drink it. Too far, and frost locks the ground before seeds can stir. Within that thin habitable margin, temperatures settle into a range. Birch forests have long depended on to unfold their seasons. Flares erupting from a young or unstable star could scorch an unshielded canopy in moments, undoing decades of careful growth. Engineers designing a birch world would need magnetic shields, orbital deflectors, or careful star selection to guard against such bursts. A single violent flare, unchecked, could strip leaves and blacken bark across whole regions. Protection from the sky, in this way, becomes as vital as protection from drought. How stretched or nearly circular a planet's orbit becomes decides how sharply its seasons swing between extremes. A gentle, rounded path keeps temperatures mild and predictable, favorable for birch forests accustomed to steady rhythms. A more elongated orbit brings harsher summers and colder winters, testing a forest's endurance year after year. Orbital shape, quiet as it sounds, shapes the very survival of a planet's trees. A single star system might one day hold several birch planets, each one a separate outpost in a shared experiment of terraforming. One world might serve timber needs, another research, another simple preservation of the species itself. Spread across such a system, these forests would form a small constellation of green and white, scattered among otherwise barren worlds. A star's family of planets in this vision becomes a family of forests too. Two suns rising over a birch world would tangle its days into unfamiliar rhythms. Depending on how the stars align, shadows might vanish for long stretches, or dusk might return twice before true dark falls. Seasons could stretch unevenly, one star dominating light in one age, both blending brightness in another. Astrophysicists studying binary systems admit predicting these rhythms remains difficult, since orbital mechanics rarely settle into simple cycles. A birch forest, there would need patience written into its very cells. Let the jaw loosen now, releasing wherever it has been holding on. Let the eyelids grow heavy, settling like something finally set down after a long carry. Behind closed eyes there is only a hushed, wide dark, asking nothing of you. No expression to hold, no words to shape. Let the face rest exactly, as it was built to rest, loose, unlined, off-duty until morning finds you again. Reaching a candidate birch planet could take decades, sometimes centuries, depending on how fast a ship might travel and how far the star lies. Crews might depart as young engineers and arrive gray-haired, or never arrive at all, leaving descendants to finish the crossing. Suspended sleep, generational ships, or plain endurance across long transits, each idea remains theoretical, since no vessel yet exists capable of covering those distances. Whatever the method, the birch seeds aboard would outlast their carriers, waiting in cold storage for soil not yet touched. Far above the forming canopy, a station in orbit could hold the maps, sensors, and schedules, guiding an entire terraforming effort. From there, engineers might track soil chemistry, rainfall, and seedling survival across whole continents at once. Decisions about where to plant next, or where a grove has failed, could pass down through relay signals within minutes. The forest below would grow at its own pace, but its overseers would watch from a vantage no ground-based team could ever match. Generation after generation, birch trees chosen for their planet could be bred for traits their Earth ancestors never needed. Thicker bark against harsher radiation, deeper roots for drier soils, or faster growth in shorter summers might each be selected and carried forward. Foresters might treat this work as patient gardening spread across centuries rather than seasons. Each new cohort would carry a little more of the planet's own signature, and a little less of the birch that first left Earth. Whether a birch planet's forest cover could ever touch its magnetic field remains an open question, and the link, if real, would only work indirectly. Roots and rain weatherstone faster than bare rock alone, releasing minerals that shift ocean and crust chemistry over deep time. Geologists suspect these slow chemical shifts might, across millions of years, alter how heat moves through a planet's mantle. Nothing here happens on any time scale a forester would ever live to witness. Across enough millennia, a birch planet's ecosystem could stop resembling the one that first seeded it. Insects arriving as stowaways might diverge into forms suited to alien light and soil. Fungi partnered with birch roots might specialize into species with no counterpart on Earth. Given long enough isolation, evolution follows its own logic, indifferent to the intentions of whoever planted that first seed so long before. A birch planet reaching full maturity might host settlements built directly into its canopy, walkways strung between trunks, grown thick enough to bear real weight. Homes could nestle among branches the way birds once did, drawing light through leaves rather than glass. Children there might grow up never touching bare ground, moving instead through a woven world of bark and rope. The forest, in this telling, would stop being scenery and become architecture itself. Cities on a matured birch planet could rise from timber harvested with the same care once given to the forests that supplied it. Managed groves, replanted as fast as they were cut, would keep the balance between growth and use intact. Buildings framed in birch might carry the pale grain visible in every beam and floorboard. A city built this way would smell faintly of the forest it came from, long after construction had ended. Given enough time, the birch of a distant planet might no longer be birch in any way Earth would recognize. Bark, leaf shape, even the chemistry of betulin itself could shift under pressures Earth trees never faced. Botanists studying this kind of divergence back home can only guess how far it might travel, since evolution rarely stays still once it starts moving. What began as a single seed carried across the dark might end as something wholly its own. Seed vaults built for a birch planet might drift in orbit, sealed against fire, flood, or blight below. Each vial could hold generations of genetic variation, insurance against any single catastrophe erasing an entire lineage. If a plague or firestorm devastated the surface, colonists could return to these vaults and begin again. The forest, in this sense, would never truly be unrecoverable, only paused. Its atmosphere, given enough centuries, could settle into a rhythm that no longer needs correction. Oxygen produced by trillions of leaves would balance against respiration and decay until the numbers held steady on their own. Engineers who once adjusted greenhouse gases by hand might find their instruments idle, the planet's chemistry finally self-regulating. What began as machinery could become, in time, simple biology. Notice the breath now, however it happens to be moving. There is no need to change it, only to feel where it goes. Each inhale rises, like something filling. Each exhale falls a little longer than the one before it. Let that lengthening exhale carry a small weight downward, out through the shoulders, out through the hands. Breathe in without effort. Let the breath out slower still, and rest inside that longer, easier release. Success, for those overseeing a birch planet's terraforming, might not be measured in canopy coverage or timber yield. Instead, it could be tracked in carbon, in how precisely the forest absorbs what its own soil and settlements release. A planet in balance would show flat, unremarkable graphs, no dramatic swings, no crisis lines. In this kind of project, the quietest chart might be the greatest achievement. One matured birch planet, documented and understood, could become a working model for reforesting worlds across an entire galaxy. Its records of soil preparation, fungal partnerships, and seedling survival might travel with colonists to systems light years distant. A forest grown once, carefully, could be repeated wherever conditions allowed. The template would not be the tree itself, but everything learned in growing it. Scattered across enough systems, individual birch planets could begin to feel less like isolated projects and more like nodes in a single, living network. Ships moving between them might carry seeds, spores, and soil samples the way old trade routes once carried grain. Each world would refine what the last one learned. In this way, forests separated by unimaginable distance could still, in a sense, share roots. A galaxy, considered at full scale, holds room for staggering numbers of worlds, sitting comfortably within their stars' habitable zones. If even a modest fraction were suited to Birch, the total could reach into the thousands, each one a candidate for its own slow transformation. Most would likely remain untouched, silent, and unclaimed. But the possibility alone gives some sense of how much room the universe leaves for forests yet to be planted. Long after the civilization that planted the first birch seedling has changed beyond recognition or vanished altogether, the forest it left behind might simply continue. Trees do not require memory of their planters to keep growing. Root systems, fungal partnerships, and self-seeding groves could carry on their business for ages after every ledger and record has gone to dust. The forest becomes its own kind of monument, indifferent to who remembers it. Even without a single human step across its ground, a birch planet's forests could persist across timescales measured in geological ages. Seeds would fall, decay, and rise again in an unbroken cycle stretching across millions of years. Mountains might rise and wear away faster than the forest itself changes character. Long after any departure, the trees would simply keep doing what trees have always done. Descendants of those original birch trees might, after enough generations, face conditions their ancestors on Earth never encountered at all. Alien mineral soils, unfamiliar day lengths, and light filtered through a different atmosphere could each nudge their biology in new directions. Bark might harden differently, leaves might narrow or thicken. Chemistry, once tuned for one planet, could shift toward another. What survives in the end would still be called birch, though barely. Given time enough to outlast rivers and mountains, a birch planet's engineered origins could fade from every trace. The straight rows once planted by careful hands would blur into wild, tangled stands shaped only by wind, fire, and chance. Species drift, soils deepen, and rivers redraw their own paths. What began as a plan would settle into something far older and stranger than any blueprint, a world simply being itself. Every birch planet answers, in the end, to the star above it. A steady, long-lived sun could let forests continue for billions of years, cycle after cycle of growth and renewal. A more restless star might shorten that story, its flares or eventual swelling closing the book sooner than any forest expected. The trees below have no say in this. Their whole future rests on a light they never chose. Somewhere back at the start of all this sits one small seed, no heavier than a whisper, carrying instructions folded tight inside itself. From that seed came bark, then groves, then forest stretched across whole worlds. The distance between that beginning and a living planet full of birdsong and shifting leaves is the entire story you have heard tonight. Perhaps your own rest tonight follows a similar shape, small and unremarkable at first, opening slowly into something whole. Let it unfold now. Good night.